So, as I've talked about a few times, mentioned VSEPR over and over again. You read about VSEPR. When I wrote the course outline for this course, I said I was going to teach VSEPR, and they sent it back to me and say, you can't just say VSEPR. You have to be specific about what you're going to teach. So I said, I'm going to teach the valence shell electron pair repulsion theory, because that's what VSEPR stands for. VSEPR. Valence shell electron pair repulsion. And I said theory because it's an explanation of why things are the way they are. It's an explanation for why things are the shape they are. It helps predict the three-dimensional geometry of molecules. And it is really, really a simple idea. Just a simple idea can lead to really complex shapes. I can turn that off for you. Turn it off. You don't want me to. Okay, the name tells you the whole theory. I'm going to say, what do you mean the name tells us the whole theory? Pairs of electrons in the valence shell repel. That's it. Repel, get as far away from each other as possible. So the electrons in the valence shell don't want to be next to each other because they're negative, right? And like charges, repel like charges. So this is just the opposite of opposites attract. Likes repel. And that's what makes it the shape it is. Those negative pieces want to get as far away from each other as possible. So the outside electrons try to get as far away from each other as possible. So see, I said the name is the whole theory. The outer electrons, pairs of electrons, try to get as far away from each other as possible.
Basically magnets.
Like magnets, north to north, yep. Like poles repel, like charges repel. From this, there's going to be some angle that's furthest away. I mean, you saw yesterday in the activity that the furthest you can get two things away was 180 degrees. That's as far away as you can get. Okay? So every time you have two, it's going to be 180 degrees because that's two pairs. That's as far away as a two pair of electrons can get away from each other. Okay? And since you've got the shape, got the angle of every bond, we can discuss that as a shape of a molecule. And the shapes I expect you to know have been hanging from the ceiling all year. There's 5 shapes around the room. They're not coming down. All the things that we're going to predict are going to start off as one of those 5 shapes. Okay? And from shape comes behavior. Think about when you did biology last year. Every time you talked about how some chemical worked, it talked about how it fit together with something else. It's about shape. It had to be the right shape to fit, right? So shape determines behavior. So the reason why we're learning shape is so we can predict how these things are going to behave. Does that make sense? Why some things dissolve in water and some things don't. The reason why most often is because of their shape. Okay? So, and it's based on pairs of electrons, and there's 2 kinds of pairs. Bonded pair, that would be a pair in a bond. And unbonded pair, that would be the pair that are not in a bond. So that's what we got to look. We got to look at that central atom and see how many pairs of electrons there are. And I slipped in, and I use it all the time because no chemist ever says unbonded pair. Instead, they use an oxymoron to describe them. You know, oxymorons like jumbo shrimp. Okay? What they call the electrons that aren't in a bond, they call them a lone pair. See, that's kind of an oxymoron. How can you be alone if you're a pair? But a lone pair. A pair of electrons not in a bond. Those two dots with nothing connecting. So the first step every time in figuring out what shape something is drawing the structural formula. Right? So let's start with 1 and see how this works. CH4. What's the structural formula of CH4? Well, we've got a couple ways to do this. I'm not going to start with the math. Carbon's got 4 dots. Can you think of how 4 hydrogens would fit on that? Hope so, yeah. So there's no need to do any math. Everybody would be happy if I just stuck a hydrogen onto each side of that carbon. This is methane, this is natural gas. Okay. So I could have drawn it this way just as well, right? Same thing. So if you look at it, it's all single bonds, and there's 4 pairs of electrons pushing away. It's Tinker Toy time again. Get the right Tinker Toys. Okay, so if I've got 4 atoms attached, to me, it looks like 90 degrees is about as far as you can get them away from each other, doesn't it? Except that's 2-dimensional thinking. In 3 dimensions, I can get them further away by moving 2 of them down and 2 of them up. And I can make the angles bigger. Hopefully you see all these angles are obtuse. They're all bigger than 90 degrees. That shape right there. The farthest you can get is more than 90 degrees. It's 109.5 degrees. So if you've got 4 pairs of electrons, they're going to be pushed at 109.5 degrees every time. Okay. This shape, where you've got 4 atoms hooked onto a central atom, it looks like a triangular pyramid. It's called tetrahedral. The prefix tetra means 4. So, and hedral means side. It's a four-sided pyramid, where every side's a triangle. For those who play D&D, it's a D4. Okay? Okay? That shape is called tetrahedral. How do you remember that tetra means 4? Well, the game Tetris is called Tetris because every shape has 4 blocks. 4 in a row, 4 in a square slid over either direction, and those L's that are 4. It's called Tetris because every shape is 4 blocks. Okay? So tetra means 4. We're going to run into it a few times this year where we're going to use that prefix tetra. Okay? So overall, it's a pyramid with a triangular base. It's a bond angle of 109.5 degrees. And everything that's got 4 pairs around the central atom is going to be this same basic shape. The only difference is sometimes it won't be atoms. Sometimes it'll be lone pairs. I could have 4 pairs of electrons. If not all of them are bonded, I can't call it tetrahedral. But it'll still be 109.5. So, The first one on your homework last night where you had to draw the structure and then tell me what shape it was NH3. So when you draw the structural formula of NH3, N wants to make 3 bonds, H wants to make 1. So that's H, 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 and a lone pair up there. Can everybody see that around that there are still 4 pairs of electrons around nitrogen? Okay? So there's still 4 pairs around nitrogen, so it's still going to be 109.5. It's just that instead of an atom, you got a lone pair. Right? Get a lone pair. So we still have that same basic tetrahedral shape. But when we talk about the shape of this, we talk about only the atoms, and this is a different shape than the first one. Because it's got 4 sides, but they're not all the same. This bottom is different than any one of the sides. Okay? So I have to give this a different name. So the name is really descriptive. It's a triangle. See, it's a triangle. It sticks up in the middle. It's called a trigonal pyramid or trigonal pyramidal. And it's the same shape as the tetrahedral, with the top removed. That shape right there, the second one hanging from the ceiling, is the first one with the top taken off. It's not taken off, it's a lone pair that we can't see. That lone pair is still pushing them down. They're still being repelled downward. The fact that these are closer together this way than that way tells you something's pushing them that way. Right? Because if they're as far apart as possible, they're going to be evenly spread all the way around. These are not evenly spread. There's a top and a bottom. Right? So something must be pushing these down. Now we draw water, H2O, you've done it a few times. With water, the oxygen has 2 single bonds and 2 lone pair. That's still a total of 4 things. Right? That's still a total of 4 things. It's just now, instead of them all, so there's still 4 things trying to get away. If 4 things are still trying to get away, you're still going to have the tetrahedral. Still have that tetrahedral, you're just not going to see 2 of them. Okay? So it's still going to be tetrahedral, but you're going to have 2 lone pairs in place of atoms. A tetrahedral with 2 of the legs taken off. The angle stayed the same, 109.5. Right? But the name has to change because this is not a trigonal pyramid. Hey, I had to come up with a scientific name for this. The scientific name for this is bent. Pretty good name for it, isn't it? Because it looks bent, right? It's not in a line, it's bent. Because that's really the only 2 options. If you've got 3 things, you really only have 2 options. They're either in a line or they're not in a line. There's no other options, right? So if you've got 3 things, they either line up or they don't. This one doesn't. It's called bent. Okay. So that seems like all the possible. Oh no, there's one more possibility. What if I had, and I'm not even going to put it on the screens. What if I had 1 atom and 3 lone pair?
That'd be an atom.
No, it's 2 atoms. So it'd still be a molecule. But what shape would you call this? linear because if you only got two things, 2 points define a line. Well, technically it's a line segment, but we'll let your math teacher tell you, remind you of the difference between those two, right? So anytime you have just two atoms hooked together, they're automatically linear. We call that the trivial case. 2 points make a line. 3 points make a line or a bend. 4 points make a triangle. Okay? So, what if you have 3 atoms hooked with no lone pair? 3 atoms with no lone pair. How the heck could you do that? Well, H2CO does that. Look at the carbon in the middle. Okay? So if I have 3, how far apart can I get 3 things? So if I talk about it in the plane, flat, right, I can take that whole 360 degrees and divide it by 3 and get 120. But we tried that with the 90 degrees, but I could move them further apart. As soon as I went out of being flat, the angles got bigger than 90. Okay? But here, no matter which way I move this ball, it's moving closer to both of the other ones, or it's moving closer to one of them, right? So if I move it forward or back, I'm moving it closer to the other ones. It's not further away. So for 3 things, 120 degrees, a flat is as far apart as you can get them. 120 degrees is as far apart as you can get them because as soon as you stop it from being flat, you're moving this one towards that one. And they're not as far away from each other as possible anymore. Reasonable? They want to be as far apart as possible. That is on a circle spread out all the way. You say, but Mr. Green, this has lone pair because I forgot to draw them in. Well, here's where the lone pair are. Right here. They're on the oxygen. And it's not the oxygen that determines the shape. It's the carbon in the middle. The one in the middle determines shape. Doesn't matter if there's lone pairs on the outside. We're talking about the central atom determines all the angles. The vertex determines the angles. Surprise, surprise. So, we have to name this shape. Okay. It's a triangle, but it's different than our other triangle. This one's flat. The other one was pointing. What's the math word for things that are flat? How does a math person say that everything's everything's flat?
Vertically challenged.
Nah. Flat, a surface in math is called a plane. Right? Along the xy plane. They talk about that along the xy plane because there's a z-axis going in and out that we never talk about until you get to 3 dimensions. Right? So the xy plane is what they describe it as. Plane means flat. Okay? Plane means flat. So they call this trigonal planar. So we got 2 triangles. Triangle pointy, trigonal pyramidal. And triangle planar, triangle flat, trigonal planar. So every time I have 3 atoms hooked, it has to be a triangle. The question is it flat triangle or pointy triangle? Those are my 2 options. What would make it, in pointy triangle, they're closer together. Right? Flat triangle, they're further apart. Pointy triangle, they're close together. What would make them go closer together? They'd have to be pushed. So if it's pointy, there's a lone pair pushing them down. These electrons push those down. If it's not pointy, if it's flat, there's no lone pair. So the lone pair makes it pointy because they want to get away from it. No lone pair, they can get further away. Reasonable? Okay. Trigonal planar. Now, if you look, this atom right here, the way I've got it, has only got 3 bonds, 6 electrons. that pair of electrons has got to be someplace else that's not a lone pair. It will happen every time when you have one double bond. I have to have 4 pairs of electrons, so the double bond only counts as 1 pair of electrons. So that CH2O So CH2O has a double bond, so it has a sigma, remember the sigma in between, and a pi, right, top and bottom. And notice that pi top and bottom, they don't want to be near that. So that's why it stays flat. Because there's a pair of electrons on the top and the bottom. So this is how pi bonding ties into that. When you have a double bond, you got the pi orbital, the pi bond above and below. So all the things have to stay flat because they'd be moving towards that pi bond if it wasn't flat. So that's why a double bond makes it flat, is because the pi bond keeps it from going up and down. And that's how we get the trigonal planar. It's got to be flat with that pi bond. Okay? So the pi and sigma actually do fit into with what we were doing before. It was about shape. Pi's make it flat. Without a pi, it's going to look like that. You can go every direction. Okay, what about 2 atoms and no lone pair? Well, how far apart can you get 2 things from each other? So I keep them next to each other, move them further, further, further. I can keep going further, further, further until here. And any direction from here is going to move them closer together, right? So furthest you can get is 180 degrees. And if it's 180 degrees, this shape is called a line. So the name of this is a linear molecule, because all 3 pieces line up. Now the problem with this is that if you look at it, the way I've got it drawn, it only has 4 electrons around here. And it can't have lone pair, because lone pair would push them closer. So if it's like that, if it's linear, it's got to have more bonds. A pi bond to make it flat this way, and a pi bond to make it flat this way, so everything stays in a long line. Does that make sense? So I'm either going to have 2 double bonds, a double bond here and a double bond there, or one end is going to be a triple, the other is going to be a single. Because a double is here, and front and back, top and bottom, and front and back. And a triple is on the same atom, top and bottom, front and back. So everything's still got to go in the line. So those pi bonds give us flat shapes and lines. 1 pi bond gets us flat. 2 pi bonds can't go up and down, can't go left and right. You got to go straight. Reasonable? Hey, that's all there is to this. Those are the possibilities. Actually, there's one we skipped. We'll talk about it. Okay. But I like tables because sometimes tables help us see patterns a little bit better. So fill out this table as we go through these. I expect this to be part of your notes when you turn in your notebook. Probably want to use it to do some of the homework until you don't need it anymore. Right? That's how, for most tables, that's how it works. You use them until you don't need them anymore, right? Like flashcards. Not like the periodic table, because we're not asking you to memorize anything on there. You'll always need that. So here's me with that table. All right. So the possibility, so number of things coming off the central atom. So we only worry about what's in the middle. Okay. So the only two types of things that could come off the central atom would be atoms and lone pair. So these first two columns have to add up, the second two columns have to add up to the first. And there's a possibility of having 4 atoms and no lone pair. What shape would give us 4 when we get with 4 atoms and no lone pair? Well,
That's a tetrahedron.
okay, so 1, the second atom is going to go as far away as possible from the first. The third is going to push those other 2 closer together. And the fourth is going to take us into 3 dimensions. And that molecule is called tetrahedral, because that's as far apart as 4 can get. So that shape is called tetrahedral. What kinds of bonds did we have there? I had 4 single bonds, right? So they were all single bonds. How many pi bonds were there? None, because you've got to have a double bond before there's a pi bond. So there were no pi bonds. And what angle did it say it was? 109.5? Under 9.5 degrees. Okay, awful. Okay, what if you had 3 atoms and 1 lone pair? That's another way you could have 4 things come off the center, because my things are atoms or lone pair.
That's still a tetrahedron.
Okay, so I remove it all, and I add 1, 2, 3 atoms and a lone pair. The electron geometry is still tetrahedral. But we can't see the lone pair when we talk about the shape. So the shape of this is a triangle, but we got 2 triangles, pointy and flat. Which one is this one? Well, it's pointy, right? So it's trigonal pyramidal. What kind of bonds do we have there? They were all single again, weren't they? How many pi bonds did I have? 0. What's the bond angle? Oh, still 109.5 degrees. Still 4 pairs trying to get away from each other, so it's going to stay 109.5 degrees. Another way you could have 4 would be to have 2 atoms and 2 lone pair. 2 and 2. So let's remove it all. Oops, go back. My mouse, there it is. Remove all. Okay, and I want 1, 2 atoms. 1, 2 lone pair. Okay. See, our bond angle is still 109.5. we're not going to see the lone pair when we talk about shape. So the shape of this is bent. What kind of bonds were they? They're still all single. How many pi bonds? There were no pi bonds because it was all single bonds, and that is 109.5 degrees still. Awful? Okay. Next one we've got is 3 atoms and no lone pair. So, looking at that, if I do this, that center atom doesn't have an octet. Everybody see? But I can't put a lone pair on to give it an octet because it said no lone pair. So that tells me that it's got to be a bond to get to that extra one. So my issue is that I put all single bonds. I really should have made one of them a double bond. And then I can have something follow the octet rule and have 3 atoms and no lone pair. Make sense? Now, bond angle here's 120. What about the shape? Well, it's a triangle. Everybody agree about that part? Pointy or flat? Flat. Right? So the way we say flat triangle is trigonal pyramidal. Triangle. Or no, not pyramidal, planar, sorry. We did pyramidal already. Planar. Trigonal planar. Planar is flat, pyramidal is pointy. What kind of bonds? 2 single and 1 double, right? How many pi bonds? Well, there's our structure, so we can see them all. There's our structure. The single bond's a sigma, sigma. The double bond's a sigma and a pi. So there must be 1 pi bond. And our angle there was 120 degrees. Right? Okay, now we got one we didn't do when we did the notes. 2 atoms and 1 lone pair. So how do we do 2 atoms and 1 lone pair? Well, I could do this and a lone pair, but I don't have my octet here. I can't add another lone pair, so I have to change my single bond into a double bond in order to make it to draw with what they described has to be a double bond instead of a single bond. That's the only way we can do it, right? So anytime you have that, there's your shape. Can everybody still see the triangle planar there? There's still that same basic trigonal planar shape. You just can't see the lone pair. How would you describe that molecule? Bent. Yeah, so there's more than one way to have a bent molecule. This is different from the other one because this bent molecule was bent at 120 degrees, not at 109.5. Because it's only being pushed by 2 things, not by 3. Types of bonds, well, that had 1 single and 1 double. And that means it had 1 pi bond, because the double bond has a pi bond. Okay with that? This is just a review of what we did a second ago. Okay, and our last one is 2 and 2. 2 and 0, sorry, 2 atoms, no lone pair. If I try to build 2 atoms and no lone pair, single bonds don't work. So before I took off and put on a double bond, but even a double bond's not enough now. So maybe it's not a double bond, maybe it's a triple bond. There. 2 atoms, no lone pair, everybody follows the octet rule, right? So there's my thing. How far apart can 2 things get away from each other? 180 degrees. What shape is it? That's a line, right? Because if I turn on the end, everything disappears. So everything's lined up. So it's linear. And it had 2 pi bonds. And it was 180 degrees. And we had a triple bond in there, right? A triple and a single. But that was only one of the ways I could get to 4. This way, there's another way to do it. Instead of having that triple, remember I had a double there first? I could have taken off the other single and made it 2 double bonds. And if I do that, I get the same shape. Shape's the same. Doesn't matter whether I use a single or two doubles, a triple or 2 doubles. But either way I do it, I'm going to make 2 pi bonds. 1 pi bond to keep it flat, 1 pi bond to keep it going from right and left. If you can't go up and down, you can't go left and right, you can only go straight ahead. That makes a line. Make sense? And so, F2S. What's its shape? Well, first I have to draw it. Well, sulfur wants to make 2 bonds and fluorine wants to make 1. So fill everything in. And when I'm done, 2 fluorines is 14 dots and the sulfur 6 more is 20. I should have 20 dots up there. And I do. There are 20 dots up there. Trust me. I've done it before. Well, 6 on the ends and 4 in the middle. There. That's 20. All right. So what shape is that? So I look at the center atom. Center atom has 2 atoms and 2 lone pair. What shape goes with that? Well, that shape is bent. Although I don't memorize it that way. I say, hey, I've got 3 atoms. There's only 2 possibilities. They're in a line or they're not in a line. Right? What would make them not in a line? What would make them closer together? Lone pair. Does this have lone pair? Yeah, this has lone pair, so it's going to bend. Right? If it's got the lone pair, it's going to be bend. Something's got to be pushing this down. That's the repulsion of a pair of electrons. Electron pair repel. So I know that's bent. What's its bond angle? Or how many pi bonds does this have? None, they're all single. What's the bond angle? Okay, I got 4 pieces trying to get away from each other. And the one that, with 4 bottoms, 4 fourth pieces getting away, 2 is 180. 3 is 120. I got to get smaller than 120, and the number smaller than 120 is 109.5. So that's when they ask you how to do the shapes. Look at that central atom. See how it matches up with your table. Does that make sense? Doable? We'll start internalizing. We'll practice this some more on Tuesday when we come back. But I do want to point out one thing. This is all theoretical. We'll talk about real bonds along the way. Oh, sorry, I had one more second. I'll take care of it on Tuesday. So homework's out of the book. It's up on School Loop. Enjoy your 3-day weekend, and we'll get in shape. We'll do some more getting in shape on